So what we learned so far? We start talking about functions, multivariable functions. We say that, hey, a function in two variables is denoted by f of x and y, and the output value is equal to z. So z is the output, and your inputs are ordered pairs, x and y. Inputs. Then we said that we can have function with 3 free variables, 4 free variables, 5 free variables, and so on. We can denote a function with 3 free variables with w, f of x, y, and z. In this case, w is going to be the output, and the input values are triples. We talked about the domain of these functions. We also talked about the range. So if you have a function in 2 variables, the domain of this function, the domain is the set of all ordered pairs such that f of x and y is defined, which is a subset of plane. Subset of plane, or R squared. Remember that the range of the function or output values is a subset of real line. And the range is subset of R. What is R? R is just your real line. If you have a function in 3 free variables, like w equals to f of x, y, and z, then the domain is part of the space here. The domain is the set of all x, y, and z values, points in the space, such that the function, the definition of the function, the mechanical part of the function is defined. So f of x, y, and z is defined. So since you have a collection of points in the space, the domain is a subset of the space itself. So is subset of the space. How do we represent the space? R to the third. Again, the range, output values, those are real numbers. So the range of the function is a subset of R. These are called real valued function. I'm not talking about vector valued function. These are real valued function because the output values are real numbers. Okay, perfect. So this has been discussed before. Then we said that, hey, after finding the domain of the function, we're interested in analyzing the function near some points. Near some points, okay, we have some limits of functions in one variable in elementary calculus. We saw that if we have, for example, function f of x equals to ax squared plus bx plus c, or a function in polynomial format. So in general, if we have a sub n x to the n plus a sub n minus 1 x to n minus 1 plus the rest of the terms a sub 1x plus a sub 0, a polynomial function, then the domain is everything. The domain is R. Remember that this function has only one free variable. So the domain is a subset of R. In this case, the domain is equal to R itself. Well, what if we have a polynomial function in 2 variables, like this function, f of x and y, be like x squared y plus xy plus 2 plus I don't know y. If you have a polynomial function in two variables, polynomial function in two variables, then again, you are allowed to plug in any number that you like for this function. This function is defined for all ordered pairs. This is a nice function. It is defined for all ordered pairs. Points for ordered pairs in the plane. So the domain is the plane itself. So when it comes to the limit of these types of functions, how do we find the limit? Just substitute the value to find the limit. We substitute the value. This is what you learned in elementary calculus. And this is what you learn in multivariable calculus. By substituting the values, you can easily find the limit of the function. Well, again, let us get back to elementary calculus. Then we move on to multivariable calculus. In elementary calculus, you learn about rational function. You learn about radicals. You learn about exponential functions. Recall that. For example, if you have a function like f of x equals to x squared plus 1 divided by x, this is a rational function. You can find the limit of this function, but first you have to be careful about the domain. The domain of the function is equal to the set of all x values such that both the numerator and the denominator have actually following and satisfying the conditions that we are looking for. For numerator, we're not worried about anything. Why is that? Our numerator is just a nice expression, but our denominator can be 0. So we have to exclude 0. Remember, you can write this guy as r minus 0, or another method representing the domain of this function was negative infinity to 0 union 0 to positive infinity. Then you can say that, hey, I can find the limit of this function at any given points. Limit of f of x while x approaches a can be calculated. Now in multivariable calculus, you have functions like this, f of x and y equals to x times y divided by x squared plus y squared. You're interested in finding the limit of these types of functions, but what is troubling here? The troubling point for us is 0 and 0, the origin. So we're mainly interested in finding the limit of these functions at troubling points like the origin. The troubling points like 0 and 0 are our focus of studying the limits. Okay, remember that when we are calculating the limit of functions, the very first step is to plug in the value. If I ask you to find the limit of xy divided by x squared plus y squared, as x and y approaches 0 and 0, the very first step, step 1, is substitution. Always do the substitution. Sometimes you're lucky. Sometimes it is an actual number. It's not in indeterminate form. Step 1, substitute. If I substitute 0 and 0, I get 0 divided by 0, which is indeterminate form. So we have to move on to step 2. In step 2, remember that you're using general paths. You might say, hey, why not plug in different values for x and y? Well, if you plug in x equal to 0 and just plug in y equal to 0, this guy says, hey, the limit as you approach to 0 is 0, but it's not the case. Unfortunately, we cannot just randomly select some paths and make the final decision. If I plug in x equal to 0, my numerator is 0, the outcome is 0. If I plug in y equal to 0, the numerator is equal to 0, and the outcome is equal to 0. So you might get the wrong answer, the wrong conclusion. To be safe, we use general paths. In this case, since it passes through the origin, the general paths that we're using can be in the form of y equals to mx. Again, remember that your job, your goal is to get rid of these variables step by step, one by one. Y equals to mx. These are just some lines passing through the origin. You can plug in 1 for m, you can plug in 2 for m, a half for m, you get infinitely many lines. So instead of just selecting infinitely many lines, you say, hey, let us use a general formula for those lines. Based on the definition of the function, you can use y equals to mx squared, mx cubed, y equals to square root of mx, and so on. By practicing, you eventually feel a little bit comfortable which of these to use. As I practiced last week, we saw y equals to mx is the best option here for us. If I plug in y equals to mx here, I get mx squared divided by x squared times 1 plus m squared. I can cancel out x squared and x squared. The outcome is a half. So there you go. For this example, if you're using mx, what you're going to have, you're going to have mx squared divided by x squared plus m squared x squared. You can factor out x squared and cancel out x squared. You get m divided by 1 plus m squared. Since the limit depends on m, so now we have the limit as x approaches 0. Since the limit depends on m, we say that, hey, the limit doesn't exist. Limit does not exist. want you to ask, how do we find the limit, actually? If a function has a limit, how do we find the limit? The very first method is just direct substitution. If direct substitution works, then you can easily find the limit. In many cases, we cannot use direct substitution. Instead, we're going to use techniques that help us to find the limit of the function. So limit and continuity. So to find the limit of a multivariable function. So first use substitution. The easiest way is using substitution. If substitution works well, you're lucky and you're happy. You directly plug in the values. Remember that you don't get indefinite form. You don't get 0 over 0. It's indeterminate. If substitution doesn't work, you can always use parametrization. Parametrization when x and y approaches 0 and 0. In this case, remember that what you learned before is x can be written as r cosine theta and y can be written as r sine theta. So this is a circle. This is just equation of a circle. So the theta is actually not important for us. What is important? R is important. What are we doing? We're taking this circle and we're shrinking in this circle toward the origin. So R, or the radius, approaches 0. This circle is getting smaller as R, or the radius, approaches 0. So we substitute R cosine theta for x, we substitute R sine theta for y, and then we take the limit as R goes to 0. So the limit of f of x and y as x and y approaches 0 and 0 can be written as the limit of f of R cosine theta, R sine theta, as R goes to 0. Then we find this limit. If this method doesn't work, we can use a squeeze theorem. Well, what was a squeeze theorem? Squeeze theorem says, well, if you have a function, general any function, this is what you learned in elementary calculus. Let's write down elementary calculus. If you have a function like f of x, which is sandwiched between two other functions like gx and hx, and if the limit of gx is equal to the limit of hx while x approaches a, and they are both equal to a number, the y value like L, then for sure you can conclude that the limit of function f is also equal to L around A. This is a squeeze theorem. You can generalize the squeeze theorem to multivariable functions as well. Very well. So suppose you have this function here. You have, this is a function that we went over last week. we use parameterization for this function. So let's take a look at this example. Suppose f of x and y is defined as x, y squared divided by x squared plus y squared. And the question says, hey, find the limit of this function as at the traveling point, which is the origin, x and y, 0 and 0. Well, if we use a substitution, direct substitution gives us 0 over 0, which is indeterminate form. We use parameterization. As you saw, we use parameterization last week. Our R goes to 0, and the limit was 0. Now, how do we use squeeze theorem? We try to squeeze this function between two nice functions like g and h. In this case, it's two variable functions that we can easily find the limit of function g and find the limit of function h. So how do we start? I'm going to take y squared divided by x squared plus y squared. Since y squared divided by x squared plus y squared, your numerator is smaller than the denominator. This is the numerator, and this is smaller than the denominator. Like what? Like a half, like a third, 5 over 9, just some numbers. The numerator is less than the denominator. So this guy is definitely less than, greater than, equals to 0, and less than equals to 1. Okay, well, this is just an algebraic fact. Since this guy is bounded between 0 and 1, the absolute value of this expression is also bounded between 0 and 1. Now, what I'm going to do, I'm going to multiply all sides by absolute value of x. Absolute multiply all sides absolute value of x. What are we trying to do? Oh, this is y squared. What are we trying to do? We're trying to create this function and squeeze that between two nice functions. Well, 0 times absolute value of x is 0. This guy is equal to x, y squared, divided by x squared plus y squared, less than equals to absolute value of x. Now take the limit as x and y approaches 0. So on the left-hand side, the limit of constant function is always 0. This is always 0. Limit of 0 as x approaches 0, y approaches 0 is 0. The limit of absolute value of x as x approaches 0 is also 0. So squeeze theorem says, since the limit from left is 0, the limit from right is 0, the conclusion is the limit of the absolute value of the function and the function is equal to 0. X, y squared divided by x squared plus y squared as x and y approaches 0 and 0 is equal to 0. elementary calculus. In elementary calculus, we have continuity. We say that a function with domain D is continuous at a point, a number like A, if it satisfies three conditions. The first condition is this point belongs to the domain. A is in domain D. 2, the limit of the function must exist at that number. Limit of function exists at A. And 3, the limit of the function and the var value and the value of the function are the same. So let us write down function f of x. The limit of function as x approaches A is the same as the y value of the function when you plug in A. We have the same thing, 3 conditions when it comes to multivariable functions. A function like f of x and y equals to z is the domain D. Remember to write down the domain. The domain D is continuous at an ordered point at A, comma B if these three conditions exist and they meet. So first of all, this point ordered pair is in the domain of the function. A and B is in D. So first you have to find the domain, check to see if that point belongs to the domain. 2, the limit of the function exists, limit of f of x and y. As we approach to A and B exists, either using pad or you're using parametrization or a squeeze theorem, doesn't matter which one, exists. And finally, the limit is equal to z value of the function. F of A and B is equal to the limit of f of x and y as x and y approaches to A and B. You have to check these 3 conditions, then say that the function is continuous or discontinuous at a point. Give us an example. Which one is continuous? So the first one is f of x and y equals to x squared minus y squared divided by x squared plus y squared. And the second one is piecewise defined function x squared minus y squared divided by x squared plus y squared if x and y is not equal to 0 and 0, and if x and y is equal to 0 and 0, the z value is equal to 0. So what's the domain of this function? You have a function, you don't see the domain, so your job is to find the domain. Take a look at this. The function, then in the second line, we have the domain. The domain of the function is the set of all ordered pairs such that the function is defined. Of course, it's not defined for 0 and 0. 0 and 0 makes the denominator equal to 0. X and y cannot be 0 and 0. So since the domain does not include 0 and 0, the very first condition is not met. 1 is not met. So it's not continuous. It's not there. The point is not there. It's not continuous.